Morning, everyone. Oh, bear with me 1 minute. I've just realised I haven't plugged my tablet in, and I'll be with you. There we go. So, welcome. We've got part 3 of Physics 2 Electricity today. We've been through most of the definitions. We've been through different types of circuit diagrams. We've been through all the sort of definitions for current, charge, resistance. We're going to sort of pull those together and start looking at them from a domestic point of view now. So how it's relevant at home, how it might be relevant in businesses, ways that we have to stay safe, and the sort of things that have been put in. We're also going to have a look at, I suppose, the national grid and how the electricity actually gets delivered to us. Morning, Jack. Morning, Tanishka. And how the electricity actually gets delivered to us. So that's pretty much where we're going to start today. Now, we need to know, I'm going to start with the national grid, and then I'm going to come back to the house and go from there. So in most cases, what we end up with is some form of generator. And apart from solar, almost everything we have in terms of power supplies, and think back to when we did Physics 1 energy, because I went through some of this then, almost everything we have in terms of the electricity generated in the UK will be linked to turning some form of generator. Now, that might be using steam, which has been heated up by a fossil fuel or by natural gases. It could be having a wind turbine. It could be a water turbine. So lots of different techniques, but it's all about spinning some form of generator. So what we start off with is, and I'm just going to do this as a flow chart rather than anything technical, because you've seen the sort of quality of my diagrams before, and I can't draw. So we end up with some form of power station. And let's just call this the national grid. Now, once we start turning that generator, we're going to start producing electricity. And we're going to produce quite large amounts of electricity. But if we started pumping that straight into the national grid at this point, and by national grid, what I mean is the collection of power lines, the collection of pylons, that basically connects the national grid, the power station, to your homes. If we just started pushing electricity straight out into the national grid, we would actually end up with a really inefficient system. Morning, Michael. We would actually end up with a really inefficient system, because what would happen is the current that leaves the power station is quite high. And we know that when we start pushing high current through a wire, we start heating up the wire. And again, I've been through that in the last 2 videos, so I'm not going to go through it all again now. But as those electrons start colliding with the nuclei in those wires, we start ending up with a transfer of energy, and what we would end up doing is heating up all of the wires that make up the national grid, which all it would do is end up transfer the energy to the surroundings. And that would make it really inefficient, and we wouldn't end up with very much energy reaching our houses. So in order to stop that happening, what we do is we go into a form of transformer. So this then goes into a transformer. So let's just do another square. Now, we'll look at how transformers work in a later physics topic. It's very much triple content, but it does come up in this sort of section on electromagnets and magnetism. So we'll talk about it properly then. I'm not going to go through the actual science behind it. But the main thing that we need to know for transformers is that these ones are step-up transformers. We'll have a step down at the other end. And what it does is it increases the voltage. So it increases the potential difference. Now, if we were just to increase the potential difference and have no other effect, that would be the same as creating energy. And because we know that our potential difference is the energy per coulombs of electrons, so per quantity of electrons. And we can't do that. I mean, that'd be amazing if we could, but we can't do that. So it has the downside of decreasing the current. So in order, the same amount of energy is moving through the wires, but the... morning, Chris. But the actual electrons themselves have more energy, but they're moving slowly. So we have the same amount of energy moving past any one particular point. Now, because we've actually slowed down the current, this is going to cause us to have less collisions. So we're going to transfer less energy to the national grid. So we're going to transfer less energy. So there's less frequent collisions, which means less energy is transferred to the wires in the national grid, so we have less of a heating effect. So let's just put down there, transfers less energy. Oh, that's almost an arrow there. I'm going to say to the wires or the power cables. So we end up with a much, much more efficient system. So then what we end up doing is from here, we're going to go to our next bit, which is our actual national grid. In fact, let me just draw a very bad diagram. So we've got our pylons. And this creates the network that covers the whole of the country. Now, there won't just be one power station feeding into this. We know we've got lots. And also what we can do is we can switch on different parts of the national grid so that we can increase and we can change the distribution depending on where the power is most needed. Some countries like Iceland, because most of the power is geothermal, they're actually looking at if they have too much, actually being able to provide electricity to other countries. So we'll actually have connections with other countries as well. So the national grid does extend beyond just the borders of the UK. But for the moment, what we're looking at is we've got this big network, power cables, pylons, above ground, some underground, and ways that we can switch it on and off. Now, at the other end of this, we need to have another transformer. So we've got another transformer here, and this is going to be our step-down transformer. So let's just go back to a different colour. This is our step-down. So if you think about the fact this is going to do exactly the opposite of what we had before. It's going to decrease the voltage and it's going to increase the current. And this is quite important because actually the step-up transformer, it increases the voltage to something in the region of 440,000 volts. So we've got this huge voltage but a very, very low current. So the electrons are moving really, really slowly. But we don't want that obviously going into the houses because one, nothing we have in a house could actually deal with it, and also it'd be way too dangerous. So we step it back down to what we need in the homes, and sometimes there'll be a series of step-down transformers. And then from here, we're going to go into our end user. So this is going to be our homes or in industry. So I'm just going to put user. So at home, and you need to know the statistics for this, the voltage that we receive is 230 volts into the house. And like I said, if you think about what's leaving the step-up transformer at 440,000 volts or 440 kilovolts, at home we only have 230 volts. So it's going to step it right the way back down again. There's another statistic that you need here. So, sorry, another value that you need. So the electricity that's coming into our homes isn't just 230 volts. We call it AC, which is an alternating current. And I'll talk a little bit about that in a moment, but it's very different to batteries, which are direct current. And they oscillate at 50 hertz. Okay, so let me just move this out of the way. And we'll just have a quick look at what we mean by AC. So AC is an alternating current. So we're going to have a look at how this is generated more in one of the later videos. So when I said we looked at magnets and electromagnets, it's also a topic that covers motors and generators. So we'll look at actually how we create an AC current then. But what we need to know for the moment is that with the exception of solar panels, anything with a spinning generator is going to create an alternating current. And what that means is the direction of the current is changing direction. So if we were to actually look at sort of a graph for this, what we would actually end up with is a sort of typical sine wave. Okay, so the direction of the current is going to be changing direction. Well, in the case of the UK, it's going to be changing at 50 hertz. Now, I think I've done a video on waves, so if you want to go back into more about waves and what hertz means, go and have a look at that. If not, we will get to it in a later physics topic. But yeah, so the electricity that's coming into our houses is actually changing direction 50 times every single second. If we look at a battery, just go down here. If we look at a DC circuit, that stands for direct current. And if we were to put this onto a graph, we would just have a single line with this one. Because actually what we've got in this case, a battery can only push the electricity out in one direction. So once we connect it off, we create the circuit and it just starts flowing around. But if you compare that to an AC current, it goes that way, then it goes that way, and it just keeps changing direction. And that doesn't make any difference for us. All of our electrical appliances at home are designed to work with it. And anything that needs a DC circuit, so if you think about your mobile phone chargers, if we're charging a battery, we need to convert the AC to a DC, and the transformer that you plug into the wall that brings it down to 5 volts and about 2 amps, that will automatically convert the AC into a DC current. So if we need a DC, then actually when our plug socket, the transformer, or the appliance will change that for us. But most appliances are designed to work with an AC current. Brilliant. So let's just move on, and I need to bring that back up because that's my notes for the lesson. So do make sure that you can remember those statistics: 230 volts and a 50 hertz AC connection for the UK electricity. It's a sort of thing that will come up either as a multiple choice or a 1-mark question, and you just want to be able to bring that straight off the top of your head and put it down. I tried to make a lot of it in terms of understanding what's going on, so we have to remember less, but there are still some values that we just have to remember, and that's going to be one of them. Now, when the electricity comes in, obviously we know that in the UK we have plugs that are 3-pin. Different plugs around the world will have different pin configurations. The UK is one of the safest. I know when I've been across to America before, they don't have an earth pin. They just have a live coming in and a neutral going back out again. Morning, Olivia. So in terms of the UK, we do actually have several safety features, and we'll have a look at those safety features now. If we look at the pins, we know we've got 3 pins, and I'm going to have a look at what these are in a minute and how we wire them up, because actually we should be able to wire them up and we should know exactly what's going on. If I turn it sideways, what you should be able to notice is that this top pin, this is the earth pin, is slightly longer than all of the others. Now the UK plug sockets are designed that if that one doesn't go in first, you won't be able to get the other 2 into the socket, because this one actually unlocks these 2. And even when you look at a mobile phone charger that doesn't need an earth pin, and we'll look at why that is in a moment, it doesn't need an earth pin, they're made of plastic, but they still have to be on there, or you wouldn't be able to get the plug into the wall. So we've got this slightly longer pin, and that's because an appliance that needs an earth pin, if there is a problem with it, you want to make sure the earth pin is connected first, and we're going to look at why that is. So if I just draw out a very bad diagram of a plug, because I couldn't find a decent diagram that I actually had rights to use, so we'll just draw out a plug that looks something like that. What we end up with is we've got our earth pin at the top, and this is going to be from inside the plug in a moment. We've then got our neutral, and we have our live. Now this is connected to a fuse, and we looked at the fuse the other day. So if I just undo the inside of the plug, and if you can see that, that's the sort of configuration we're looking at. What you'll also notice down the bottom here, there's actually a cable clamp, which is another safety feature. Now, if you have a molded plug like we were looking at the other day, and there's my molded plug, you'll notice actually there's no way of taking this apart. So what's actually done with these ones is the wires will be connected to the pins, and then it will be, the plastic will be molded around it afterwards, so we can't physically take it apart. And that's fine for most people, because most people won't need to change a plug. But if you're changing the wires, or if we actually get damage to the cable here, then what we'll actually find is we need to put a new plug on. So in that case, what we'll do is we'll swap one of these for one of these. And this is what I'm going to show you now. So what you'll notice is there is a series of screws, and this is where the wires are going to be connected to. Let me just grab my screwdriver for a minute. So, I'm not going to wire one of these up now. I will do a separate video, probably just a couple of minutes long, just so we can see. But what I can do, if I just undo this for a minute. So what we've got is we've got this wire clamp at the bottom that I've just loosened off, and you'll notice there's a gap going in. So our wire, the electrical cable, goes into there, and the wire clamp clamps down to hold it into place. And that just means if you've got something plugged into the wall and you accidentally knock it or you trip it, it's not going to pull some of the wire out and expose bare wires. So that's our safety feature number 1. So let's just write this on here. We've got our cable clamp. And what you should be able to do is talk about each of the safety features and why it's important. In the case of all plugs, we're looking at a plastic case. And obviously we know that plastic is a very good insulator, which means if anything has come loose inside the wire and we go and touch the plug, we're not going to get a shock. We have our earth pin. Oh, sorry, let's get rid of that. We've got our earth pin. And we know that if we look at our plug from a sideways point of view, there's our earth pin. Our other 2 pins are here. And our earth pin is going to be longer. And we'll look at the function of the earth pin in a moment, but that's another one of our safety features. We have a fuse. And if you remember back to last lesson, in fact, I think the last couple of sessions on this one, when we started looking, we sort of drew the diagram and the circuit symbol for a fuse. And we said the reason that it's important is because if anything goes wrong, the fuse is designed to melt if too much current is being pulled into that appliance. So we've got our fuse. This is going to be our live pin. And this is going to be our neutral pin. Oh, can't spell today. There we go. So that's the main features. So what we have coming in, we've got our wire coming in, so let's just do that. Now the wire has a plastic insulation coating, so a plastic coating. So it's double insulated, so there's a plastic layer around the outside. Running through the middle of it then, what we have is 3 other wires. We've got a blue wire, and that'll be covered in another plastic coating that's blue. So we have each of the wires inside has a plastic coating that is insulated, and then we have another plastic coating around the outside, so we have a double insulation. That one makes it stronger, and it also reduces the chance of us getting a shock. So the neutral wire is going to be blue. I do have a brown one. Our brown wire is going to be the live wire, and that gets attached to the fuse. And then going through the inside of this, we have, it's actually yellow and green striped, but I can't do a yellow and green striped one, so I'm just going to do yellow and green, 2 wires going in like that. So we've got a yellow and green striped, and if you want to just make a note on that, I'm just going to put striped wire going to the earth pin. So you need to know the colours of each of these wires. So we've got a brown wire going to the live pin, to the fuse. We've got a blue wire going to the neutral pin, and with the earth pin has a green and yellow striped wire. So that's the sort of main features. Now if we were to look at the national grid, let's just draw out a basic circuit and look at what's going on. So we've got our AC current, and that's coming in, and what we actually end up with is the electricity comes in down the brown wire. So this is our live. It then goes to the appliance. So I'm just going to do our basic light bulb for a minute. And it goes back out down our neutral wire. So if we just label those on there, this is live and this is neutral. Notice the earth wire hasn't been used in any way, shape or form. And that's what I was saying, when you're looking at your mobile phone, a lot of the mobile phone chargers, the earth pin will be plastic because it's not used at all. So I'll come on to what it's designed for in a minute. But the main thing we're looking at is we've got the live coming in and we've got the neutral. And the electricity flows around there in exactly the same way we've looked at before. So what we end up with, if we go back and we start talking about this in terms of the circuit diagrams we had before, we have 230 volt potential energy or potential electricity coming in. we have 0 volts leaving. Okay? Now, if something goes wrong, and this is where the safety features start kicking in. So let's imagine something goes wrong inside it, or we have a wire come loose, and we start drawing too much electricity. So let's just say somewhere around here, we get a wire come loose, and that connects to something else. It doesn't make any difference what it connects to for the moment, but all of a sudden, we've now created, almost like a parallel circuit, we've created an additional feed. So we've got electricity flowing around the circuit, and we've got electricity going this way. And what that's done is that increases our current. Now, a couple of things should happen at this point. One of the things that should happen is too much current is being drawn, so the fuse should melt. So we should end up with a melting fuse. And when the fuse melts, that stops the live feed. And that's one of the reasons why when we're connecting up a plug, we should always connect the live feed to the fuse. So we need to make sure we do the correct one. If we connected the neutral up to it and not the live feed, if anything went wrong, the fuse wouldn't melt. So the electricity would carry on flowing into the appliance, or into, it could be somebody being electrocuted, or into something else, which could then risk a fire. Because it doesn't actually have to be somebody being electrocuted. It could be that it's connected to something else. We're now drawing too much current. The wires start getting hot. Think about what we said about resistance. We've got more frequent electron collisions, more energy being transferred. The wires get hot, and we could create a fire. So we can have electrical fire. So by the fuse melting, we need that's a safety feature. So we've got to make sure that it's the live feed that's connected up to the fuse. Something else that could happen is when we actually start looking at, if you think about your fuse boxes at home, if we've got one of the newer fuse boxes, which most houses do now, not one with a fuse, and I shouldn't really call it a fuse box, we're talking about one of the ones with the trip switches. So if you think about, we've got a series of switches, and what they'll do is we've got this switch that's like that. What happens is if we get more current being drawn, these switch down and they flick off. Now these are called, or one of the names for them, RCCBs, and it stands for residual current circuit breaker. And what they do is they measure, so they measure the current coming in equaling the current, actually let me just move that somewhere else. So these things measure, sorry, that one. Current in equaling current out. And as long as those values are the same, our circuit switch stays up. As soon as those two don't equal each other, and if you think about it in the terms, yeah, MCBs, I'm not entirely sure what the M stands for on those. Some of them work in slightly different ways, Tanishka. So yeah, but they work pretty much on the same principle, that if you think about our main circuit, if it's a continuous circuit, if we were to put an ammeter anywhere on this circuit, we should have the same readings. So what these circuit breakers do is they measure the current coming in and the current coming out, and as long as they're the same, our switch stays up. But the second we get any discrepancy in that, and the only way that could happen is if electricity was going somewhere else other than the appliance, as soon as the current changes, the switch trips down. Okay, so yeah, they're just using miniatures, but they're still RCCBs, they're just smaller versions of them, okay? So yeah, as soon as those change in terms of current, the switch trips or flicks down. Okay, yeah, I'm not going to try and say that too quickly. So that's the safety feature, and they've replaced the fuses on the circuit board, because years ago what they had was another fuse the same as they had inside a plug, but they would be mounted in a fuse box, and if anything happens, what you'd have to do is pull out the old style fuse, and I haven't got one here to show you, and there'd be a piece of wire that's melt, and you would unscrew the piece of wire, you'd thread a new piece in, screw it up and put it back into the fuse board again, and it would all be done very manually. Unfortunately, some people were sort of silly enough that if they didn't have any fuse wire, they would put nails in them or a piece of tin foil. and it wouldn't have the correct rating, which means we increase the likelihood of something going wrong, or we increase the likelihood of a fire or somebody being damaged. Now, these RCCBs or MCBs, they're designed to work so fast, they will literally trip in a millisecond. So even if it was a case of, if you can imagine somebody running a lawnmower over an electrical cable, that person should only get an electric shock for a fraction of a second, still enough to do some serious damage, but they're not going to stay attached to that line being electrocuted until we've got enough time for that wire to melt. So it's a much faster, it's a much bigger safety issue. Now, we've spoken about all of these, but I still haven't spoken about what the earth pin does. So I said that mobile phones don't have them, and a lot of appliances like that don't. So it depends on what the appliance is. Generally, what we're talking about when we're looking at using earth pins is something with a metal casing. So it's usually anything with a metal casing around the outside. Or we're looking at bigger appliances. So we're looking at things like fridges and freezers. We're looking at things like washing machines. We might be talking about light fittings in homes. But generally anywhere where if a wire came loose inside the appliance, if you touch the appliance, you would get an electric shock. So if we had something like a washing machine, let's just say, and this is going to be quite a rough diagram, let's just say we've got our electrical cable coming in, and then that's going to be connected to whatever the circuit is. If we had a random wire come loose and touch the outside of the casing, this outside of the casing would now become live, which means anyone touching it is going to get an instant shock. What you normally have, though, with all of these appliances is the earth pin will be connected, so there'll be another wire going from the case onto that earth wire. Now, somewhere in the house, that earth wire will be connected either to a copper rod that it will be driven deep underground, or often it'll be connected to the copper water pipes. It doesn't make any difference. The main thing is that what we have outside is something with a 0 volt potential. Very, very low potential. Because that means as soon as that wire comes loose and touches the case, electricity takes the path of least resistance and it's go to wherever there is the lowest potential difference. And in this case, it's going to be the ground. So it's going to be dragged straight to ground. That's going to cause a huge spike in current, which is either going to cause a fuse to melt or it's going to cause the RCCBs to trip. And hopefully that will happen before anyone actually touches it. So that's really important we get our heads around that. That we can understand how it works. But if you think about it, that's quite important, because if we have a damaged appliance, that sort of earth pin being slightly longer, as soon as we push it in, the very first thing that's going to be connected is the earth pin. So the outer case is going to be connected to that earth feed, which means if there is something wrong, the electricity is going to be taken straight to ground. So hopefully we don't get damaged. So one of the things I suggest you do after this session is either re-watch what I've done or have a look at these lesson notes and make a table on a revision card somewhere listing what the safety features are, but then the important thing next to it is explaining how it's a safety feature and how it prevents either fire or how it prevents injury. There was an exam question a couple of years ago, and I'll just run through this now. Basically what it had was a diagram of an electric shower and somebody working on it. And the question was to explain why it's important that the electrician that was fitting the electric shower turned the mains electricity off before he started working on it. Now, the explanation for this was the fact that the live potential coming in was 230 volts and the potential of the electrician was 0 volts. So therefore, if he didn't switch it off and he touched a live wire, what was going to happen was that a connection would be made from the 230 to the 0 volts. We now have a potential difference, so we're going to get a current flowing through the electrician. And that was the sort of level of detail they wanted on it. So we've got this potential difference between the 230 volts and the 0 volts. Brilliant. Right, let's just move somewhere else on here. That'll do down there for the moment. So the next part when we're talking about domestic electricity is to talk about, let's change back to black. talk about power. So every electrical appliance you have in your house, somewhere written on there, it will tell you the power rating. And our power rating will be measured in watts. Now, there's a few formulas that are linked to power, and we're going to be looking at all of them to make sure that we can actually understand how they are. But what power is telling us is the rate of transfer of energy. So it is the rate that energy is being delivered to an electrical appliance. So whenever we have anything with rate, one of our formulas is always going to be divided by second. If you think about speed as the rate of travel, if you think about current is the rate of transfer of charge, and that was coulombs over second. So whenever we're looking at this one of the formulas is always going to have a divided by a time, because we need to obviously work out how much is being delivered per time. So one of the big formulas we need for this one is power equals, so I'm going to put the change in energy, or you can put down work done divided by time. So we've got watts is our change in energy divided by time in seconds. So I think to give you sort of a few examples with this one, if I look at the charger for my laptop, on the back of it, and I wonder if we can see this. Very, very small. I'm not sure if you'll be at the camera, but we'll be able to focus on this one. But right at the top, where my finger is pointing here, if it will focus, you can see the power rating, and it says 45 watts. So that means that every second that my laptop charger is charging my laptop, it is using 45 joules of energy per second. So we can put this down as an example. So we're using 45 joules of energy per second. And you can sort of compare this to different appliances. Anyone who's got a smart meter in their house, and that's one of those ones that you sort of plug into the mains and it monitors the energy that's being used, it's quite interesting to plug different appliances in and work what happens. I know I can have most things turned on if I use ours, and it sort of just drifts up into, I don't know, I mean, I think ours is sort of colour rated. I mean, we can have values on there as well. It drifts up into orange maybe at times. We start putting the electric shower on, and we very quickly start going into the red section on there. Sorry, switch a kettle on. If we put the electric shower on, it goes completely off the scale. Now, to give you an idea, so that's our laptop. If I look at the kettle, my kettle is 1.5 kilowatts. So this means it's using 1,500 joules of energy per second it's turned on. So with a lot of people, they say only boil the water that you need. And I know a lot of people, and I'm guilty of this at times myself, the first thing I'll do is fill the kettle up and I'll turn the kettle on. Now, I might only need just enough for 1 cup. So there's no reason to fill the whole kettle up. And you can buy the kettles now that obviously only heat up just enough for 1 cup anyway, and it'll just dispense 1 cup's worth. And that's quite useful because actually, the more water that we have to have turned on, and if you think back to specific heat capacity, so just as a link to our energy topic, energy that's transferred is going to be equal to the mass of the water that we want in kilograms, multiplied by our specific heat capacity. Now for water, this is 4,200 joules per kilogram degrees C, multiplied by the temperature change. So actually, if I add half a kilo of water, and bearing in mind my cups are quite big, so I probably do have half a kilo of water that I'm trying to boil at this time, I might be taking this from, oh, that should be a temperature, yeah, so temperature degrees C. I might be taking this from, let's just say 5 degrees Celsius up to 100 degrees Celsius. So in this case, what we're looking at is a 95 degree change multiplied by 4,200. And let's just do a calculation and we can sort of work out how much energy is being transferred. So we've got in here 0.5 kilograms. Let's just work out how much energy is being transferred here. So, where's my calculator gone? There it is. 0.5 multiplied by 4,200 multiplied by 95. So that means in order to boil 1 cup, enough water for 1 cup only, I'm having to use 199,500 joules of energy. So if my kettle is on, we can work out how much time this is going to take. And this could be an example for an exam question, which is why I'm sort of going through this one. Again, I'm just using sort of basic stats, and sort of feel free to do this yourself with any appliance with this. My kettle is 1.5 kilowatts. So I'm going to divide that value by 1,500. That means it should take me 133 seconds to boil the water. So I've just sort of gone through and I've just done a very quick calculation with that one. But 199,500 joules, and that's if I boil just enough water for 1 cup, which is probably enough for this. If I'm boiling the whole kettle, I think my kettle takes 2 litres of water. That's about 2 kilograms. So just to give you an idea for the difference for that one. Wrong one. Let's do that one. So if I do 2 times 4,200 times 95. So this is, let's just say that's 1 cup. If I do the full kettle, we end up with 2 times 4,200 times 95, which is going to equal 798,000 joules of energy. Okay, so we've got a massive, massive difference in the amount of energy needed from going from 1 cup to 1 kettle. Now, just to put this back into perspective in terms of other appliances, so you can have a look at any of these. So it's worth having a look at things like if you play an Xbox or better still a PS4 or with a PC. If you look at the power supplies on those, you can actually work out how much energy it's using for every second that you're actually playing a game on it. So it's worth actually going through and sort of just going through and doing those calculations. You could look at a hairdryer. You could look at the calculation, you could work out how long that you're actually drying your hair for, and then you can actually feed these back into a calculation to work out actually how much energy you've used. So an electric shower, so I'll put electric here because not all of them are. Let's just say I think the electric shower that I've got fitted at the moment is 8.5 kilowatts. So therefore I'm using 8,500 joules of energy per second. So you can imagine, actually, if you're somebody, she's never going to watch this, so I'm going to talk about this. If you're someone like my sister, who might spend 20 minutes in a shower, then actually we can go through and we can do the statistics, the calculations for this, to actually work out how much energy she's going to use if she was in our house and if she had a 20-minute shower. So the first thing we need to do is to work out how many seconds. So 20 minutes times 60 means she's in that shower for 1,200 seconds. So that means she's going to be using 1,200 multiplied by 8,500 watts. So let's go back and multiply that. So that means that if she had a shower in our house and she spent her usual time in the shower, she's going to be using 10,200,000 joules of energy in the shower. Okay, so that's almost 10 megajoules of energy just having the shower. Now, we possibly won't get time today, but we can go through and we can actually have a look through at, we can work out the cost per unit of electricity, and we can actually then link that back into how much this would cost. Because with a lot of houses, with most power companies, what they'll do is they will have a cost per kilowatt hour. And we can sort of have a look and we can actually sort of go through and we can do those calculations. So you can work out how much it would cost per shower you have. And it's quite a useful exercise to do. But like I said, after this, I strongly suggest that one of the things you do is you go and pick 4 or 5 different appliances around the house. And it could be a fridge, it could be a television, it could be a games console, it could be whatever. Look at the power rating that's written on there. Think about how long you actually play it for, and look at how much energy is being used. What would be worth doing then is going through and speak to your parents, find out how much the cost of energy is. So we can look at the cost of energy. And I can't remember what ours is at the moment. I should have looked it up. So the cost of energy, and that will generally be pence per kilowatt. Per kilowatt hour. And you can work out how much it's going to cost. So kilowatt hour is equal to the energy used, sorry, the power of the appliance you're using in kilowatts, multiplied by the number of hours that you've been on there. Okay, so I'll do the example for my sister in the shower again. She's a sister, so I'm allowed to pick on her. It's absolutely fine. We can go through and we can do the calculation for this. So we know that the power rating was 8.5 kilowatts. If we look at the time for this one, 20 minutes is, what's that, 0.3 hours? So we can multiply that by 0.3 hours. 0.3 hours? Yes, third. Yeah, 0.3 hours. 8.5 times 0.3 is going to be equal to 2.55 kilowatt hours. Let me just see if I can find a very quick, it won't be for my one. Let me just put UK, just do a Google search, UK cost per kilowatt hour and see what it comes up with. Okay, so the first one that comes up, and I don't know how current this is, but the average cost of UK for electricity per kilowatt hour, if I put average cost per kilowatt hour in the UK, is equal to 14.37 pence. So what I can then do is I can multiply those two numbers together and say that every time my sister has a shower, multiplied by 2. That's going to equal 36.6 pence. Okay. Now that doesn't sound too much, but if you think that hopefully she's having a shower every single day, let's work out what the cost of that is over a year. So we can go through and we can multiply that by the number of days in a year. So that's going to equal 1,000, this is in pennies, remember, 1,374.9 pence. So in other words, her showers are costing her about £138 a year if she had a 20-minute shower. So I've gone through and I've literally just used data that's everyday average data, and I've gone through and I've practiced these calculations. We're going to be putting more of these online. I was talking about in a meeting today, we're going to be putting more of these sort of questions online to Google Classrooms over the sort of coming weeks. And one of the ideas we've got is to do some longer questions. And then what we'll do afterwards is we'll post like a walking talking mock, with it be a quick 5-minute video of us answering some of these questions. So watch this space. It's something that's going to be coming up very, very soon. So let's just go back up to where we've been looking at this. So we've got this idea then that power is the rate that energy is being transferred, and we should be able to work out the amount of energy being used for a particular appliance if we know the power, and we know the amount of time it's been turned on. The other sort of thing that we could do as well is if we knew how much energy is been transferred and how long it took, we could then go through and use that calculation to actually work out what the power rating is. Now, there's another couple of formulas that we need to know for this one. So I'm just going to put those down now. So our power is equal to our voltage, our potential difference, multiplied by the current. So that's one of the ones that we need to know for this one. Just bear with me 1 minute. There we go. That's fine. Just want to make sure that was off. So one of the skills you need, and you should be able to do this for maths, and this is very much needed for the higher level papers. So I'm just going to talk our way through this, but we should be able to combine multiple formulas into one. So we know, because it's one of the most, I said before, it's one of the most common formulas we have, the voltage equals current times resistance. So I'm going to substitute, let's get rid of that. I'm going to substitute V for this. So that gives us power equals times current times current. Okay. In other words, that gives us resistance times I squared. So you need to know these two, but if you know these two, you should be able to work out how we get to this one. If you don't, make sure you remember it, but it's one of those ones that we should be able to substitute in for to make sure that we can actually do. The other thing that we should have a look at with this is we can start trying to link in some of the other sort of ideas we've got. I mean, for instance, we know that voltage is equal to energy per coulomb. We know actually that our current is equal to the coulombs divided by time in seconds. So we can actually go through and cancel these ones out, because actually, if we sort of look at the top formula up here, we can go through and substitute in, and we can actually get back to our formula of power equals energy divided by time. So just be aware that all of these formulas are interlinked, and it starts making sense. If we know that power is energy divided by time, we know that voltage is linked to the energy per coulomb of electrons, then those should be able to start seeing that actually, if we increase the voltage, we're going to start delivering more energy. If we increase the current, we're going to start delivering more energy. And if we're delivering more energy at a faster rate, then our power has gone up. Okay? So spend a bit of time just trying to get your head around those sorts of things, and actually just work out how that's all linked together. And again, if you've got any questions, so I'm just looking over at my notes to make sure I haven't missed anything with this one. If you've got any questions, sort of put it in, and I'm more than happy to come back to this next time when we have a look at it. Okay? So, this week we're sort of doing 50-minute videos. So I'm going to keep this one to 50 minutes, which means I've got like sort of 2 minutes left. So just really to go back through what we've been talking about, and then on on Friday, I'm going to finish off looking at static electricity. So make sure you've got your heads around the power grid, the national grid, and how it works. If you need to go back through the videos that we did for energy, have a look at how the power station works and how that energy is delivered to our homes. Bring it in then and have a look at what a transformer does, and make sure you're happy with the idea that we increase the voltage, because by doing that one it decreases the current, so less energy is being transferred to the national grid, and that's going to increase the efficiency of our processes. We then have to step down the voltage again, which brings the current back up, but that brings it down to a safe level of 230 volts for our homes. And when we do that, it's an alternating current at 50 hertz. Go back through, like I said before, have a look at the plug and the electrical wires in our homes, and make sure that you can list all of the safety features of all of the appliances and the wires, and that you can actually talk about how it's a safety feature and how it keeps us safe. And that's both in terms of stopping electrocution, but also stopping fires as well. So make sure that you can talk about that. And if you've got your head around properly about resistance, how resistance increases when the wires heat up, we should be able to work out the fact that actually if the wires heat up too much, there is a possibility of the wire and the plastic around the outside of them catching fire. So all of this sort of ties into the previous session that we've been doing. Make sure you can talk about the use of the earth pin. So the fact it's longer to make sure it connects first, and also it unlocks the other 2 pins. And that's the reason it does that is the fact that if the wires come loose inside an appliance, if the outer case becomes live, it's not going to connect with you. It's not going to create a fire. It's not going to draw too much current. The electricity is going to be taken to earth, and that's generally either to a copper rod in the ground, or it's going to be to the copper pipework. Make sure you can talk about the RTCBs and how they're looking for differences in current in and current out. Definitely make sure that you can do the different colours and the purpose of each of those wires. So we can talk about that as well. Finally, do some calculations. Go through, look at some electrical appliances in your house. Think about how long you use that electrical appliance for and work out how much energy is being used. If you want to use the average cost of electricity that I put down here, which was, what did I put that down? 14.37 pence per kilowatt hour. Go through, do some calculations. How much is it costing to use that appliance? Because that's the sort of thing, realistically, they're going to ask you to do in the exam. And I can set you exam questions on this, but you can do them yourself. And as I said before, when we look at 40% of your exam questions are going to be on unfamiliar circumstances. And it's going to be applying this sort of knowledge to real world situations. And you don't need me to set you the work for that. You can literally pick up anything and think about, how do I use this in a real life situation? How much is it going to cost me? How much energy is going to be used? How could I reduce the energy use? If we're looking at helping the environment, what sort of things could we use for less time? And things like that could be actually only boiling enough water for 1 cup of electricity. Because as we proved here, that makes the difference between 200,000 joules, near enough, to nearly 800,000 joules of energy just by boiling less water. And if everybody started doing the same thing, that means straight away that we're going to have a much lower energy usage, which means the power station's going to have to work less, and we're going to actually reduce the amount of energy that's going to need to be generated to power the UK. So you should be able to see, actually, we've got links to energy topics. We've got links to environmental topics in biology. There's links to chemistry topics when we start talking about power consumption and combustion. We've got links to efficiency, which goes across all of these, and everything ties in quite nicely. I know in the exam boards, they will often ask you questions that link multiple topics, multiple subjects together. There's a lot of maths in this, so we've got links to other subjects outside of science as well. I know they've brought in geography with this as well. So just make sure you're comfortable with it and that you understand what's happening, how it's happening, and why it's happening. And if you need to, write down a list of questions of things you're not sure about or that you don't understand the links between, drop them to me in an email, or on Friday, I'll do another Google Meet, jump onto Google Meet and ask me those questions so we can talk about them face to face. And if you're having problems with Google Meet or anything else with that, again, please let me know in Google Classroom or by email so that I can address those issues. Right, that's me done. Have a great day, enjoy the rest of the day, and I'll see you on Friday for the final part of Physics 2. Take care.